afternoon. My name is Koen Casier. I'm from IBBT, which is associated with the Ghent University and with other universities in Belgium. It's an interdisciplinary and inter-university research center. We do research on network technology and all types of research going from protocol side up to the software and interaction between in the networks, distributed systems and stuff like that. But my research topics are on the techno-economics. And the techno-economics is really about if you have a novel technology, if you have a new software application, if you have a new network, if you look at fiber to the home or you look at wireless networks, what will it cost? Where, in which situations is which solution better than the other one? Taking into account the fact that if you don't spend the money now, it might be better to take the solution in which you only spend gradually. Even if this takes more money, the money spent later on is better than spent in the beginning. And I did my PhD research and finished my PhD on the economics, techno-economics of fiber to the home. But next to that, I've also been involved in a lot of wireless techno-economic researches. And one of those I'm extending here is building a business case for wireless sensors in a factory setting. But it's a long title, I know, so I'll go step by step. So what's a factory setting? That's an old factory. It's very old. I found it on Google, it's like 1930. It's like in the 30s, something like this you would find in a factory. So that's a factory setting. There you have all types of machinery, and which is important. You have the different people working. In a historical setting, there's the different people working in a factory, and they all work, they all have their own work, and there's one or several people controlling the work of those. It evolved and you got more and more machinery, but it was more like a workplace in which different people were working on were handling the machines, and there was some control in the back end, looking if everything went okay, if the machines were working all right, and some like that. And gradually increasing the machinery, increasing the control and the gaining input in the factory setting evolved into something like this we see today. And that's a realistic factory setting. I found that it's like in the year 2002, something like that. This is the factory setting. And what is important is that you see that the automation didn't stop. There's more and more automation in there. And what is even more important is that you don't see the people anymore at the robots. There's only the automated robots, but you don't see anyone looking at those robots. And that's where the sensors come in. So for building such a good automated factory setting, they need a lot of sensors. And most of the time, this is just an example of sensor. So we'll focus on the sensors. It's important, if you look at the sensors, you have to make a distinction between there's sensors who need instant output. If something goes wrong in a robotic arm, it might fracture itself, might break components, might do a lot of harm. So these are millisecond or even sub-millisecond control, or 10 milliseconds, something in those ranges. And then you have a lot of background sensors, like sensors who measure the temperature. If you measure the temperature of the environment, it won't just lapse into 10 degrees hotter in just a few seconds. You can tolerate a monitoring of once a minute, something like that. It makes an important difference. And the other one is the criticality. Is some environment variables, even them, you would consider if the temperature goes above 50 degrees, then you have to shut down everything. In other environment variables, you just want to know. You just want to know how many times this happens. You just want to learn from it, but you don't have to react on it, and it's not critical. So that's the main important differences in the sensors. Why do I say this? Because if you look at both axes, you can define the accuracy of the sensor, so the cost of the sensor, the amount of the sensors to be placed in one location. Perhaps you need survivability and 2 sensors at the same location. And the refresh rate. I said, do you need it to be in milliseconds? Do you need it to be in half a second, seconds? Or can you cope with just a minute refresh rate or even more? Do you just want to monitor the environment? For the workers, do you want to monitor it for the machines not to break? Do you want to monitor it for the production not to be slowing down? It's a really different. And to come to the point of this presentation, it will make an important difference in the installation approach. If you're talking about milliseconds, you choose another installation than if you're talking about seconds or minutes. And it will also cost, if we're talking about the refresh rate and we're talking about wireless solutions, the more refresh, the more measurements you have to send out a second will wear out the energy, the batteries. And so it will have a large energy cost or battery power usage. It will have an impact on that, and that's the second important thing. And then I've talked about the factory setting. I've talked about the sensors in the factory, why they are there, and now I talk about building the business case. And that's something from the paper. If you'd like more information on that, I would suggest you look into the paper. It's the full business case. It's the full model for calculating what a sensor network in a factory setting would cost. But important is, there's 4 parts in there. First part is the equipment and installation. How much will the sensor cost? How much will it cost to connect them? Either way, wired or wireless, up to the controllers. Second part is looking on, if you have wireless sensors, you need batteries to power these wireless sensors. How much will the battery power cost you? The third part is looking on, if you have any breakage of cabling, of sensors, of battery shortage, power shortage in a wireless sensor, then you need to do maintenance. And how much will the maintenance cost you? And then the fourth part is, it's a loss due to offline time. And that's considering reliability. If you install a network and it's not as reliable, how much downtime will I incur with the new network? How many times could I risk in a year? How many hours could I risk to go offline with a production or a part of the production? And that loss can be calculated. How many workers are idle? How many machines are idle? How much would it cost? There's cost functions in there for a sensory, for a setting in a factory. They know how much it costs to be offline for like an hour. And it makes a big difference between the continuous running factories and the non-continuous daytime running factories as well. So, and that's on the business case. And I'll go into a little bit more detail in the first part, the equipment and the installation. We make the distinction between the wired and the wireless. So the title is about building the business case for a wireless sensor network, but it's unfair to just build a business case and have no benchmarking. So the fact that I also considered a wired sensor network is because I need to know whether the wireless sensor network will cost more or less. In which cases will it cost more or less, and which are the main parameters who make the distinction between both business cases. So in the wired situation, I look at cabling. It's the first part. I look at, so you go from the sensor to some aggregation points. I have to take into account the cost of the aggregation point. How many aggregation points are there? And then finally, to calculate the cabling between the sensors and the aggregation point. So in the middle is the aggregation point, and I have like 8 by 8 sensors, 64 sensors. How much cabling would I need? I just used here an analytical assumption. It's not easy to look for how will the cabling actually run, that I can make estimations using an analytical model. Most probably it will be better because they will be more clustered closer in the machine, but you're never sure. In the wireless case, we'd have to take into account first, at the sensor side, we need to install a wireless transceiver. That's clear. We can choose between different solutions. I'll talk about that in just a few seconds. The second part, as I already told, is the battery power. You need to power the wireless sensors in order to make it able to just click them on or screw them on a machine or on the wall. You need to have a battery pack to power them. You won't consider installing wireless sensors with the wire to the electricity network. That would be just ridiculous. And as I mentioned, considering the transceivers and the final controller, you need to decide which technology to use. We considered the Zigbee a solution, and additionally, we also considered a situation in which you use Zigbee in cooperation with a sensing engine. So a sensing engine is like a slimmed down Wi-Fi listener. It's not a Wi-Fi transceiver. You can just listen to the Wi-Fi signal and identify whether you'd have a collision or not, in order to make the Zigbee more reliable, to be able to transmit into the windows in which the Wi-Fi isn't transmitting. So you don't have collisions, you don't have retransmit from the Wi-Fi, so you avoid the collisions, you have a better reliability. So we make the distinction between Zigbee and Zigbee without sensing and Zigbee with sensing. Why didn't we use the Wi-Fi? If you look at wireless sensors, the very important thing is the energy. And if you look at the energy, a Wi-Fi transceiver just consumes much more energy because you have the full protocol, you have the higher bit rate, and you don't need that. It's okay just to have a low power consuming sensing engine just to know whether there's something on the Wi-Fi and schedule your next Zigbee transmission. Considering the power, the energy consumptions, it's not only, I've done the calculation here, how much will batteries cost? And it's not fair to say a battery will cost you per watt hour, will cost you that amount. It's not as if you're buying one battery, you're buying 1,000, you're buying, even if you have to replace them after a year, you're buying like 2,000, 4,000 batteries at a time. And it makes a big difference. As you see, I've just run some tool for extracting publicly available data about the costs of batteries, and I fitted the least cost and the highest cost. And as you see, the R squared is very high, so it's a good fit for the values. Of course, it could be ameliorated in the future as well. But that's like the cost of battery if you install more, and it will make a difference if you install larger networks. And the third part is just on the maintenance, and in this we took into account that you have a failure rate of the sensors. So you'd have to go for replacing the sensors. You could have a breakage of a cable, inflicting failure of many sensors, and you need to do maintenance of the batteries. You need to replace sensor nodes and batteries. I have to mention we did not take survivable networks into account in which you have multiple sensors measuring the same thing. So that's an extension we hope to make in the future. And then considering reliability, I talked about the Zigbee without sensing and the Zigbee with sensing. So it's just not true, not good to imagine a factory setting in which there's no Wi-Fi. There will be Wi-Fi from the surroundings, from anyone carrying a smartphone. There will be Wi-Fi in the air. Collisions will occur. And even if you only have a 10% Wi-Fi load, which is on there 5.4 megabit a second, without a sensing engine, without a possibility, and and with the retransmits of the Wi-Fi and the collisions with Zigbee, you'd have like over 80% of packets lost. That's not the real focus of the work in this presentation, in this paper. I've not done the calculations here, and I've not done the measurements, the real measurements here. I've trusted the measurements of a colleague of mine. These are published results on wireless sensing versus non-sensing. So if you look at the sensing, you'd have a much higher, much lower packet error rate for transmissions, even at a higher Wi-Fi background. So again, that's how we built the business case. Now we can look at evaluating this business case. What did it learn us? So at the current wireless costs, so this means at the current costs we found for Zigbee transceivers and for a sensing engine, we can calculate the different costs, the costs for the fixed, the costs for the Zigbee with sensing, and the costs for the Zigbee without sensing. And what you see here is that it's just the extra investment on top of the lowest solution. So at the 0% is the lowest solution. This means that at this point, there's two curves on here. You'd have the fixed background. You'd have the background, which is in green. And you see that the fixed is the most costly solution up to more or less 10 sensors. And then the Zigbee with sensing becomes more the most costly solution because of the sensing engine you have to add to the cost. If we're looking at the fixed critical, so for the critical sensors, with a refresh rate of 100 milliseconds, then we go into, at 9 sensors, the fixed solution is the lowest cost solution. That's for the current wireless costs. If you compare it to, so as I said, 10, and you can go up to, the lowest solution is there without sensing engine, up to 40 sensor nodes. If you would install overall wireless with sensing, you would, in the background sensing environment, incur an extra cost of up to 20% for 100 nodes and 30% for 100 nodes in the critical. But if you look at the future wireless costs and you say prices will drop within 5 years up to 50% of what they are now due to integration of the sensing engine into the Zigbee chipsets, due to just higher manufacturing rates of the Zigbee and the integrated chips. So if we calculated the costs then, we got the conclusion that you could go up to 20 critical sensors in the lowest solution with Zigbee, including sensing, and you could go without sensing up to 100. The lowest cost solution would go up to 100 wireless sensors, background sensors in a factory setting. And even if you would install everything from start and just upgrade, and you would use wireless with sensing everywhere in the factory, the first 20 would be the lowest cost solution, and you would only risk to incur an extra 15% cost on top of the fixed solution. So conclusions. The current situation clearly indicates that wireless sensor network in a factory setting with high refresh rates is just very limited installations. You'd have less than 10 critical sensors in a factory setting. It's just too little. You'd have less than 40 background sensors. That could be feasible if they're only for measuring the real background and you use a wired solution. But if once you have the wired solution, you just attach the background sensors to that and you're cheaper. Still, if you look in the future and you would have a price drop on the Zigbee and integrate it with the sensing engine, then you could go up to 20 critical sensors in the network and up to 100 background sensors in the wireless network. which would make sense. And only if you start with wireless with sensing, you would only risk later on, and it's an extended risk, so it's not the risk you take at the beginning, only risk 10 to 50% extra costs when extending the network beyond the 20 critical and 100 non-critical sensors. So one last conclusion is that this paper presents a reusable calculation model, and we plan to reuse it in other situations as well. There's more than just a factory setting. We set the factory setting because it's really limiting, really pushing the limits of a wireless sensor network. But could be home environments as well. And in those environments, you'd have less critical sensors, so meaning that you could easier go with wireless sensors, and you could have city networks as well, city nodes, city wireless networks as well. And we are working in the first steps in a project which is really looking into how to deploy a city-wide wireless network, and that's the comparison they will make as well. How many wireless sensors can we install, where can we install them, in which range can we install, and should we make a buffer, for instance, with a wired sensor part, just buffering different areas. And that was my presentation on building the business case for wireless sensors in a factory setting. If there are any questions, feel free to ask.